Ladies and gentlemen, I would like to introduce to you AurasenIHD. We are the internal hardware design team, and our team members consist of Sal, Nico, Patrick, and my name is Wilson. Now we work under the company Aurasεν. That consists of 3 key members: the CEO, Don Bowie, the CTO, Dan Wiggins, the CFO, Mark Bowie. Now I'll hand it over to Nico.
Thank you, Wilson. We're going to look at our problem statement, which is really the backbone of our project. Basically, with our problem statement, we are taking the technical fine-tuning process involved in programming hearing aids and making it more accessible to the non-technical hearing impaired consumer, giving them the ability to program their own hearing aids rather than visiting the audiologist. Our hardware and internal circuitry design will allow the programming of the hearing aids as well as an interface with the sound card and amplifier configuration to output sound to the user for testing purposes. So this is how we interpret and organize our client needs. First, as a group, we comprise a list of questions here on the left. We then interview our client and write down his answers, and then later in the middle column, and then later discuss as a group and interpret the needs of his answers. And then as you can see here, we highlight the constraints of the project in blue. Also, we highlight the requirements in green and what we need to do next in red. This is our objectives tree. This is a way to organize everything we want and to show the qualities that we want in our hearing aid system. So in the first here, we see that we need our product to be marketable, efficient, portable, and user-friendly. The next tier describes the contributions of the first tier, such as quality of sound, low power consumption. It needs to be versatile and natural and transparent. Now we're going to take a look at our engineering requirements and specifications. I'm not going to go over all of them, but I definitely want to highlight a key component. As a team, we went and visited an audiologist locally in Riverside, Dr. Donna Esquit, and she took the time to show us and teach us all about the process of programming hearing aids. And she definitely made it very apparent the importance of frequency response and how it must provide an adequate range for the human ear, including speech and everyday sounds. She showed us a graph similar to this, showing the range of frequencies of sounds that we hear every day. After that, we concluded that our product needs to be able to work within a range of 5 Hz to 10 kHz. Every product on the market has standards. This is a list of standards that we comprised that are applicable to our product. A very popular standard today that is used for communication and power supply between computers and electronic devices is the USB. And we will definitely be utilizing USB in our product. Other very important ones are audio streaming interface and audio file formats. An extremely important one is reproduced speech quality. We want to be able to emulate real life sounds and speech as much as possible to the users. And I'll pass it to Patrick.
Thank you, Nico. Now that we have been introduced to the main concepts of our project, allow me to highlight some of the constraints that we are facing. First of all, one of the big constraints that we previously encountered was the use of the new sound program, because this program was drawing too much current, almost 500 milliamps when it's in an idle state. However, this is not an issue anymore because we recently received another programmer, which is called the HiPro programmer. This one I'm holding. This is more efficient in terms of the power management because one of it draws half of the current, the other one was drawing. And also, since it's part of the constraints, so for any engineering project, there might be some changes to the constraints. And so was the case when we received this one. When we first saw it, we just met as a group and look at the pros and cons, and also did some measurements. And we finally found that there is a very good engineering to go on with the hypo, because this one is an industry standard programmer, which is more adaptable to the many hearing aids that are being used nowadays. And so one of the questions might be, why is there a constraint, since it sounds more beneficial to us? Where there are so many constraints attached to this programmer. For example, the operating temperature, the relative humidity, the air pressure, and the warm-up time. And I want to emphasize the warm-up time because we want our product to be very fast enough when it's stayed on. So the warm-up time in this case is less than 20 seconds, which is very good. And more about the constraints, the ASP, which stands for Aurasonic Platform, emits stereo sound. And we are now using in headphones. And this is because we want to emulate the natural hearing environment of our customer. So, and another very good feature of our product is that we are providing detachable cables, and this to help the customer easily connect or disconnect the device. And this is where the magnetic coupler comes in, and we are trying to work in collaboration with the mechanical team in order to implement this feature. Now I hand over to Risa.
Thank you, Patrick. As part of our concept generation, we decided to form a morph chart. This is our morph chart template. So as you see here, the means are the function. The function is here on the left side, and then we have several ideas that can help accomplish our function. So let's look at a specific example. Look at outputting sound to the user. Outputting sound to the user has been identified as our function or our desired accomplishment. Listed below, you can see several different ideas that we can use. These are the means or the ways that we could accomplish our overall function. So we have headphones, external speakers, and built-in speakers. Headphones. The user could get a pair of headphones with the product that they can wear when they're going through the testing process. External speakers. We could rely on the user to have a set of speakers at their home or wherever they are that they can connect to the programmer in order to go through the testing process. And lastly, the idea of building speakers until the actual programmer was proposed. Of these three choices, we decided that having built-in speakers would be the best idea because it would make the testing process as uniform as possible, as well as adding portability to our programmer. So we went through this and we made 3 different morph charts. This is the first one. When you look at all the different morph charts, you'll notice that these are highlighted on all of them. These are constraints that were defined by the client. So they are absolute, and this is what we're going to, in all the different types of variations we have for our product, this is what we're going to go for all of them. This is the second morph chart we made, and this is the third morph chart. So after evaluating all 3 morph charts, we decided that this one would be the best idea. So in deciding what element we should, or what proposed mean we should use for each function, we made scoring tables as part of our concept selection process. Here on the left side, on the first column, we identified objectives that would contribute toward our function. So here we're analyzing power distribution, as you can see by the label at the top. And power distribution is important because we're limited to using the amount of power produced by a USB. We're not running it out of a wall socket, or we don't have an external power supply. So one of our limiting factors is how much power the USB puts out. Now these are all objectives, and we assign the objectives a weight on what we feel is most important. Now after going and looking at all the different options, we kind of did some research and evaluated on how well we felt that they would be able to accomplish the objectives. And that's where we put the score within the scoring table. Then using the simple equation, we came up with an overall score for each of the different elements. So as we can see here, the LDO/dual switch has the best overall score in the power distribution category. The next one we looked at was heat dissipation. And heat dissipation was important to add add to our efficiency. If we look back at the objective screen, you can see that efficient heat dissipation is listed under the efficient category. And that's because we want to optimize the operating condition of our programmer, as well as make it safe. So as you can see here, using the structure as a heat sink got the best overall score in the heat dissipation category. The last one we looked at was communication. Now this is the way the programmer talks to the computer. So basically it's the cable that connects it. So after analyzing the different choices we had, the mini USB came up with the best overall score. And now I'll hand it over to Sal.
So let's look into functional decomposition. So this is taking all the abstract ideas we've been talking about, like cost, marketability, and efficiency, and putting it into something you can visualize. So here's level 0. As you can see, the user provides a computer, a laptop or desktop running Windows, and plugs into our device, the Aurasen Sonic platform. Aurasen Sonic platform, or ASP, connects to internal speakers, as we decided already, and external hearing aids, which we are making the connectors for. So let's open the hood of the ASP a little bit and see exactly what's going on in here. As you can see, the very first thing you see on the left is our input, and that is the USB port. Everything is running off this. So data and power. For data, you can see that the USB hub is the one that is distributing the data from the computer to the sound card, the programmer, and an optional flash memory that we have yet to realize. But also, we're taking power. So that's another important part. We have a power management section right here. And as you can see, the USB hub itself draws some power. And also, the sound card is drawing power. What the sound card is just like a glorified digital to analog converter. And it takes the digital data coming from your computer and makes it analog. The reason we want analog is use the amplifier right here to amplify an audio signal and be able to drive some stereo speakers that we have on the ASP. And that will output sound to the user. Another function we have is using the programmer, which itself draws some power. And the programmer is provided to us, as you see the iPro over there. And we are to integrate that into our system, and that becomes very critical when we're determining our power management section. So let's look a little deeper into functional decomposition by going into seeing what we have to decide for each component. So what we did was compare every component. So for example, right here, this is the sound card, with different other components. As you see, the PCM 2906, 2900, and various other different types of sound cards that we could possibly use. And then see, okay, compare and contrast them. We want to see what is better, what do we want for our system and our purposes. So let's just look at a couple things here and how we calculated it. For each component, we determine exactly how many peripherals will go around the chip. These are different types of sound card chips, but each one has to have peripherals around it, such as resistors, capacitors, inductors, diodes, or other peripherals like low-pass filters. We determined how much each one needs and found the corresponding size and price for each one, multiply that. That's how we get total price and total board space. So it's a rough estimate, be able just to compare. Before we actually build or order these parts, we want to compare beforehand, so we do a rough estimate like that. Also another thing to look at. So we are comparing these two right now, and we want to see what features we want to have. So actually this one has, looks like it has better features, right? The SPDIF interface. But actually, the SPDIF interface is what allows you to do a volume or a mute on the sound card, which can, in some applications, be good. But for our purposes, we don't want the user to have these buttons on the side of the ASP and messing around with the volume or the mute all the time and getting confused with what's going on. That's being handled by a lot with the software and internally. So actually, we do not want that feature. So it looks like, using this comparison, we decided on the PCM 2900C as our sound card. So for example, we did that for each of our level 2 components here and decided exactly which chip we're going to use for each. And just this is like our overall system right here, level 2. And you can see that from each one we have a block diagram for each. So each one we're going to have to create a circuit schematic for. But before that, Patrick.
Thanks, sir. Talking about the budgets and the parts ordering, we have a total available budget of $250, and we use this budget to purchase all the components that we need. For instance, we purchased the Class D amplifier, the USB hub, the sound card, and other essential parts that we need. For example, the resistors, capacitors, etc. And after we decided about the budget, we submitted a budget proposal to the Chief Financial Officer. Mark Bowen is here. We have that. But in order to do so, in order to well clearly communicate and explain our budget processing and the parts ordering, we developed what's called the Bill of Materials form. And this highlights the detailed information. For instance, it gives the vendor part number and also the total cost. And so far we have total cost of $174.56. And this, we are good. We don't worry about ordering new parts if needed, because we are still less than the total budget which is available now. Now I'll hand over again to Sir.
Thank you, Patrick. So now we're going to put some meat to the bones. We're going to actually show you our prototype and actually see the design flow that we used. For our purposes, internal hardware team, we took the approach of using a schematic, generating that with a lot of electrical engineering concepts, generating a breadboard, and then finally going to a finalized PCB version that can fit inside of the AurasenIHD platform. So let's look at the schematic first. This is an example of the level 2 block diagram. And from that, we generated a schematic. And as you can see here, this is the chip, and it has all the peripherals around it. We decided exactly every single component, the value, how to connect it, what to use, all with a lot of research and before we ordered. So once we determined that, we got the okay, we went to the breadboard, but before that we had to order all the parts. So we used a website called DigiKey, where they have a lot of components, pretty much everything we need, and that makes it all from just one vendor, so we don't have multiple shipping costs. Everything's just one place, and this was a good place to find exactly what we needed for each component. So once we got the parts ordered and they came in and arrived, we were able to build our breadboard. So this is the USB hub right here, and as you can see, every node and every wire is labeled exactly how it is on the schematic. So for us as a team, we can be able to interpret exactly what's going on here. And actually, each node is labeled so we can attach what you see here for testing purposes. But one of the challenges we had to overcome was using surface mount chips. Surface mount chips are these tiny guys way in there that don't really readily connect to a breadboard. But we found a solution called SmartBoard, where it allows you to solder surface mount chips directly here and then breaks it out into breadboard spacing. So that's what you can see right here. And for each of the chips, we did all that for all the surface mount IC chips. So once we did that, we were able to test and analyze what's actually going on inside the breadboard. Instead of having like the PCB, you can't really test it. Right now, it's really easy just to connect a voltmeter or an oscilloscope onto this and see what's actually going on inside. As you can see here, we have signals. We're measuring voltages, currents, making sure our power is good, making sure our USB communication is good. And that's what we can do with the breadboard. One challenge we had to overcome was the clock source. For digital communication, the clock of the computer has to be synchronized to the clock of any device that's trying to talk to it. So what we did was look into different options like quartz crystals and resonators. But with our limited experience, we found that this was a challenge to figure out, and the data sheets really don't give too much explanation on what's really going on with the clock source. So a lot of research is going on into how we can get the computer and the USB hub to communicate very well. So that's one of the challenges we're currently overcoming. But once we do that, we can go straight to the printed circuit board, or PCB. This is our preliminary design already we made in Eagle, and this allows us to go from a schematic that we generate to a printed circuit board layout. And this is our preliminary design right now so far. And it's all on the computer, so in case we determine, oh, we need a different resistor here, we can just go in and change the value or change the size of what we need for the printed circuit board. So that is coming along. And once we do that, we can send it to what we call a board house to get the PCB printed onto a silicon board with traces, copper cores, ground planes, and we're able to solder everything on there. And it takes these three giant circuit boards and puts it all into a PCB a size that can fit into the ASP box. Patrick?
Thanks, sir. Project management is an important factor to the progress of any engineering project like ours. And so, in order to manage our project, we are using two very important tools called the work breakdown structure and the Gantt chart, and we have updated this accordingly. And with the help of the WBS and the Gantt chart, we can be able to zoom in some of the important upcoming dates. For instance, one of the most important dates is the beta testing of the school financing, and this is happening mid-March, and final testing too. And here we conclude our presentation, and now we open time for questions and answers.
A little bit on the interface. You said you still have an interface that you have to complete. I believe it's between the programmer and your circuit board. Yeah.
Yeah. This is actually from the USB hub to the computer. The USB hub, as you can see here, we can plug in 3 downstream devices, such as the programmer, the sound card, or a flash memory if we wanted to.
Yeah.
So we're trying to get the USB hub to talk to the computer. Then it could talk to the other devices.
Okay. Have you been able to make the connection between the programmer and your card?
Not yet. That's why we're determining.
You have to have that first, you say?
Right.
Okay. Did you see that this is no impossible situation then? That you'll be able, you think?
It's definitely possible. Just a little research is going into what kind of clock source we can use.
Patrick, you said you've spent $174 so far, and you've approved a budget of $250.
Yes.
Now you're halfway through this mid-semester, so are you going to be spending the rest? Are you winding down what you're purchasing, or are you going to need more products?
We can have everything we need now, but since when we are doing testing, we may end up breaking some resistors, capacitor, and those are not
replacement parts.
Yeah, replacement parts, and they're very cheap. So
all right.
We are thinking that will still be within the range of the budget.
But you'll be well within the budget, and you're confident of that?
Yeah.
Okay, well, how about your printed circuit card? When you go out to the printing shop to have that made?
Dan expressed to us that he has already something in mind for that, that he knows a place that he's used to working with. So yeah, we're gonna get that information from him, how much it costs once you send in the files to get the printed circuit board.
Okay.
I believe he said we could do like a multiple amount at a time. Just in case. So
Oh, yeah.
It's kind of like a package thing.
Because that, the turnaround's going to be
Right.
significant there, because you're coming up on your testing dates.
Right.
Yeah.
That's like in the consideration.
So back here in the corner, can you summarize, Sal, again at the moment, what are your technical difficulties?
Technical difficulties, one was the smart board idea, which was successfully overcome except on one thing. Everything turned out good except for the amplifier. The chip itself is really small, 5 millimeters by 5 millimeters square, and our soldering iron has a very fine tip, but we believe that it didn't solder perfectly onto there because the amplifier is not yet completely working. And we narrowed it down to exactly that the chip is not drawing current, so it needs to just make a connection. So we're looking into just redoing the solder on this guy. That's one challenge, and the other challenge was the clock source. So there's the only two left that we have to overcome right now.
I don't mean to, put undue pressure on you, but how much of the system is working right now?
Everything except the communication from the USB hub to downstream devices like the programmer or the sound card. The computer detects the USB hub, so it's able to talk with it. Except downstream devices, it's not being able to recognize yet. And we narrowed it down to the clock source. That's one thing we have to synchronize.
Are you able to simulate, as you preparing a printed circuit board, and I know dates are coming close, are you able to, in my experience, sometimes what goes on in a printed circuit board could be somewhat different than what happened in the prototyping bed.
Right.
Are you able to simulate any part of that printed circuit board design, to get some confidence, it's going to work before you create it?
Before we print it. That's the idea of what we had with the breadboard, but we do know there is, you're condensing all this into a confined space, and
it's it's a relatively complex system.
Right, and a clock here might be interfering with the electromagnetic field of the other clock. That's too close. So we're going into looking to research like, okay, where do you want to place stuff, basically? And research is going to, okay, we want the power here, and we want that as far away from the clock source so they don't interfere. And stuff like that. Our research is going to that. Simulation-wise, we're just kind of basing off research right now. Not being able to exactly simulate, we haven't looked into a solution like that. But
So in other words, you put your confidence on the working circuit on the breadboard, then you directly send it out.
Right. But also take into account, once we put all this into a confined space, what might happen. And we're just looking up, what other people have done, and other things we should look out for.
Any questions?
When you get your circuit board made, are you prepared then when you find something else to cut some jumpers and stuff like that?
Yes.
Okay.
We've actually already experienced that with one of the evaluation launches we have. Just one thing came off and we just made a jumper. It was really easy to get things going that way.
Okay.
If it's printed and then we don't have to wait for another turnaround time, we could just edit it directly.
That was my question again.
Yes.
Yeah. Because that's you're coming up.
Right.
You're going to be time limited.
Any more questions?
On the flash memory, can you just a little bit, it sounds like that's something you'll put aside.
Right.
And what penalties do you get then because of that?
Dan expressed to us that very beginning, he just said, later down the line we might be able to add a flash memory. So I want you guys to act like you are doing it, but just not look into actually plugging it in.
Yeah,
See
okay.
if it works.
So you're saying the port is there.
The port is there, and it's actually, we set it, customize it to be an attachable device, or permanently detachable device. We just have to change one pin from high to low. And everything's made so that it could be integrated, just in case.
Okay, what functionality do you lose by not having it?
With not having it?
Basically the memory, because what the idea was of the flash memory was that someone would have all their settings saved on a flash drive.
Yes.
So then when they go through the process of programming the hearing aids, they can just plug the flash drive in and it'll kind of shorten the process. So what we'd lose is functionality-wise in that is kind of, I think, the way that the memory is going to be loaded again, because I believe they were trying to check into an online database, and then if somebody perhaps doesn't have internet connection, then they might have to go through the whole testing process to be we adjust their hearing aids. So flash memory would kind of be like a very safe way to ensure that someone will always know their settings safe.
They go back to.
Back.
Okay, but it won't stop them from having multiple settings at any one time.
Back down.
Well, let's thank our presenters once again. We're out of time.